So similar to the previous talks, we'll have two parts. One part is the background on channel modeling. The second part is something related to research. So we talk about generally what do you mean by a channel modeling, what are the things we need to look for, and what are the basic things of properties of channel. Let's understand them from fundamentals. And the second part is I'm currently working on with my students on air-to-air channel model. So I'll tell you what I have done so far. We haven't published the work yet, but you can see the relationship between what we know, what we are learning now in the first hour will be applicable or will be relevant, and they are necessary to understand a research problem that I'm going to present in the second hour. So in fact, also wanted to mention that the talk by Sundar Vanka on Saturday is actually very timely in the sense he gave in the first slide itself, he gave a simple idea about how path loss, channel gain and shadowing, how they can be combined in a very simple formula. So now we are going to learn how do you get the channel gain. In fact, how do you model a channel impulse response. That is the key for understanding something further. And I also wanted to mention that I use the book, the content from Wireless Communications Principles and Practices by Rappaport. That's an excellent book actually. Okay, especially when you are looking for communications, I strongly recommend to use the book. There are many books, but especially for the very basic ideas about, like for example, channel propagation. This is what we are going to spend time today. And you remember the plot that Dr. Vanka showed you on Saturday is something like this. Okay, so he considered an abstract model, but I'm actually going even more fundamentals. And the reason is, I see that some of you are in undergrad school, and you might not have gone through some of these basics formally. The second thing is, Professor Vanka's topic is more rigorous in the sense it talks about the mathematical foundations, and and for that you can't go and talk about basics. So I'm going to fill that, fill the gap, and then tell you how how these ideas and how these fundamentals are helpful if you decide to work on new models. All right. So take a look at this slide for a minute, and then we'll get into the details. The purpose of the next few slides, or first this hour rather, is to understand the characteristics of radio wave propagation, and then how do we measure the quantities. Some of the quantities are metrics. So more specifically, when you look at the propagation, you will see small scale fading, large scale fading, and let's go over them slowly and then understand the ideas here. Typically, when there is a propagation from transmitter to receiver, the first thing is that we all know, we talk about the free space loss. So in addition to that, in addition to that, you will also have what we call a lot of reflections, and the signal actually will go through a transmitted signal that is sent out by any radio, will go through all these physics, reflections, diffraction, and scattering, and all these have to be accounted for. Now, how do we take into account? So first thing is, obviously you cannot go very meticulously and see how you cannot characterize each of them individually, But in general, by doing a lot of experiments, like practical demonstrations or experiments, you can capture the essence. So that is the summary here. Now we're going to look at. First is, due to multiple reflections, waves travel different paths. So in addition to typically a direct line of sight, most of the time, yeah, you can assume there is a direct line of sight, but sometimes you may not have a direct line of sight also. Okay, but ideally you can assume along with the direct line of sight, you also have several non-line of sights. So we'll go through, we'll look at them visually in a minute. To begin with, this interaction is called multipath fading, or the physics is called multipath fading. And why is that multipath fading? Because as the signal travels through any distance, actually, because it's an electromagnetic wave, it travels at the speed of light, and then it will naturally have a path loss, which is proportional to d square. Okay. So that is one thing. But on top of it, you're going to see a lot of these effects, and those are reflections, diffractions, and scattering. So in general, you can categorize into two types of fading. Large scale fading, large scale propagation models predict average signal strength over long distances, and then small scale fading typically mean they are rapid fluctuations of the received signal strength over short travel distance or short time duration. So there are two major aspects. One is for long distance, for long propagation model, long scale propagation model. Second is small scale. And if you look at this picture, you will also see a basic idea of what do you mean by small scale. Okay? So first thing is large scale. Look at the blue curve. That talks about, in general, when the signal travels a long distance, primarily it captures the path loss, free space path loss. On top of it, you have all these small scale fading, and the scale actually refers to the wavelength of the transmitted signal. So here, when you say small scale, you have to keep in mind we are referring to, with reference to, we are actually using the reference of a wavelength of the signal. Okay? So that is one key idea that you have to remember. So in general, you can summarize, there are large scale aspects and small scale fading aspects. So first thing that we need to know, free space propagation. In fact, in the presentation that Dr. Vanka showed, it's very simple. In one line or very succinctly, you can capture this free space loss by simply saying it's a function of d power some exponent. Typically, it's d square, especially if it is free space. But if the environment is urban or more complex, then the exponent may not be 2. It's something bigger. So again, in simple terms, you can say path loss, especially free space path loss, is a function of d square. Okay. So that means you can say it's a function of d power minus 2, right? Keeping other things aside, we're only looking at the in terms of distance. What is what you call path loss exponent? You can say in free space it is 2 or minus 2. But then if the in urban environment, like there are so many buildings, or sometimes even in a rural environment, there are a lot of, for example, trees or shrubs. In such scenarios, it is also possible that the path loss the path loss exponent may be anywhere between 2 to 4, or sometimes the worst case could reach 5 also. So that means that the path loss is going to go through a lot of RF signal will go through significant losses if the environment is very complex. So remaining things are straightforward, right? But let's go through them very quickly. It depends on, of course, wavelength or frequency. Then you know the formula from lambda frequency to wavelength, which is lambda equal to C over F. Then GT and GR refer to gains of the antennas, transmitting antenna and receiver antenna. In simple terms, you can say if it is isotropic antenna, you can replace them with 1. and then PT is the transmit power, and then PR is the received power. There is also another term here, that L is a system loss. What does it mean? Something to do with hardware and other factors related to generally the antennas and RF system hardware part. But if you ignore this, and if you set GT and GR equal to 1, it's very simple that path received power depends on transmit power, the wavelength, and distance. Those are the key things. Again, I'm reviewing this for the benefit of people who haven't taken this so far. Okay? All right. And this is a little more details about gain of an antenna that depends on the effective aperture of the antenna. And then we said L equal to 1 indicate no loss in the system hardware. So we talked about L before. So if you set L equal to 1, which means that you're ignoring any system level or hardware losses. There is also another term called EIRP. EIRP stands for effective isotropic radiated power, and that is equal to, your EIRP equal to transmit power times G of T. Yeah, again, all this information you can see in the book. You are getting a quick tour of, I think, at least a couple of chapters from the book in this first hour, and these are important so that we can go to the next research topic, so that otherwise you won't be able to understand that. Stop me if you have any questions, but this should be clear actually. Okay? All right. Now this idea of path loss for free space, including antenna gain. If you include antenna gain, it is in terms of dB, path loss equal to 10 log PT by PR. Okay. And that's actually 10 log GT times GR lambda square 4 pi square D square. So this is coming from the previous slide. So if you set antenna gain equal to 1, then it's much more simplified. It is path loss in dB is 10 log lambda square by 4 pi square D square. This is very simple and straightforward. But notice, when you look into representation in dB, you are going to see a lot more than one term. We say dB, sometimes we say dBm. What's the difference between dB and dBm? M refers to in milliwatts. You are using power in milliwatts. So dBi is there. dBi used for antennas. With reference to isotropic. I stand for isotropic, with reference to isotropic antenna. So same way dBm refers to with reference to milliwatt as a reference. dBi refers to antenna gain actually. So that refers to with reference to isotropic antenna, what is the channel gain. There are other things too. Okay, there are more such terms. dBi. Okay, we will see them, but those are easy to follow. All you need to do is, of course, we have. You can search on the internet, or you can search on many other sources. But keep in mind that when you're doing the computations, you have to be very clear, or what units you can add, what units you cannot. So it's important to make use of, understand the notations, understand the units very clearly. So these are straightforward. Okay. Now let's look into little more into physics. When we talk about line of sight and non-line of sight, let's review them for 5 minutes. Here, there is a vehicle. Mobile receiver is in the car, and there is also another mobile vehicle, but we are only use it for explaining or illustrating the reflection. So here is our transmitter. Here is the receiver. So now look at, there is a direct path. So that's what we call line of sight. And there are many paths. Let's look at one of them is reflection. Look at this. There is a signal here from cell tower hitting a house, and then it is reflected from the house to some other obstacle or some other building, and then it is reflected again. So that is one path. That's typically maybe one of the longer paths. And then there is another one from the building. It's reflected to the mobile vehicle, and then it is falling on like an object and getting scattered. Then one more is there is a building that is being reflected, from which the signal is being reflected, and many more. So you can see, first thing is there is a reflection and there is a diffraction here. There's another example of diffraction is here. Then there is a scattering. So one signal is coming reflected, and then there is another reflection, and then it is going through scattering. So first thing is you can see the complexity of it. We can draw a lot of diagrams like this. At the same time, it's difficult to capture what exactly happens to your signal. It is not possible. So the only way you can is somehow do some experiments, do some simulations, and come up with an abstract way of capturing this physics. So no matter how you do, what you do, it's not possible to really know what exactly happens to the signal. But doesn't mean that we cannot solve problems. Okay, there are ways to do some experiments and come up with a general, capture these concepts in a generic sense. Okay. But the point of this slide is to make you understand these ideas. What is reflection? What is diffraction? What is scattering? Okay. There are some more information about these physical phenomena, and the textbook, of course, gives you a lot more details. All right. Okay. Now, there is a model called reflection, a two-ray model. This is what practically used. In fact, when I wanted to develop the air-to-air channel modeling, this is the model we are using. We start with one ray and then adding more rays later. But to begin with, the fundamental level, whenever you think about channel modeling, it doesn't matter whether it is on the ground or air to ground or air to air. These ideas, this concept is useful. So this gives you a simple means. Assume that there is a transmitter at altitude of h sub t, and there is a receiver at the altitude of hr, and then you are showing only two paths. One path is line of sight, the other is non-line of, only one line of sight. What's happening is the signal is being reflected from the ground. Okay, I'll show you after 1 hour in the next lecture how we started like this for a air-to-air channel model. So the nice thing is, if you understand all these ideas and spend some time, probably a couple of weeks, going through the 2 chapters in the book, you will be ready to do any new channel model on your own. Okay, so there is a tool called Insight that I'm using. It costs money. No, I think academic discount was like about $7,000 I'm paying for Insight. Maybe there are for students, or maybe there may be more discount if you reach out to the company. But in general, that tool also, it implements all this physics internally. So we don't have to worry about modeling this. But modeling on your own is also important, because understanding how channel models work and then trying to develop the mathematics behind it will help you to look at the theoretical aspects. And then if you use a simulation tool, I believe in MATLAB also it is there. If you already have a MATLAB, look for whether you can model this in MATLAB itself. Okay? So MATLAB also provides you these tools for modeling channels, and Insight is more specific for this kind of things. INSITE. So my point is, you need to understand the concepts. You should be able to understand the theoretical modeling, how to do the theoretical modeling. At the same time, you should also use some tools. That way, you have a multi-pronged approach to develop or to do some research. But without knowing all this, you cannot do research. Okay? And the other aspect is you always have to have a theoretical component. Otherwise, anybody can do experiments. Just because you do 100 experiments doesn't mean that you are able to show something. If you have a hypothesis that you come up with, if you want to test, if you want to show that this hypothesis actually works, you have to have theoretical concepts and support and show how the experimental results validate or verify what you come up with. And then if there are any discrepancies, you should be able to figure out. And that is actually the research. When there is a discrepancy between theory and practice, you ask the question why there is a discrepancy and answer them. In that process, actually, you will find some interesting things. So it's not enough if you just only do the theory or if you just do the experiments. You need to do both and see the connection. Whether the ideas that you have in mind are working. And if they work, then it's good. If not, then you should be able to see what is the reason, and then you refine your models. So that is the process you have to follow. So here, you're only showing two paths, and obviously you know that the line of sight is the shortest path, and then this path is reflected. So that's why it's longer. So in simple terms, all you need to do is you need to look at for example, for example, let's say if you are computing the received power, then the received signal is coming through two lines, two paths. So you're supposed to take into account of both. So I'm not actually here is supposed to be like energy, E for energy. But for now, we will not worry about this, but focus on the general idea of how can you explain, how can you consider the reflection from the ground or maybe from buildings or maybe some other objects. We talked about several things, right, in the last picture. It's not just one reflection. We talked about a lot of reflections. And not only, in fact, in this case, it's not even from the ground. It is coming from different buildings and then from other vehicles. So you should be able to figure out what is the context. For example, if you are simulating an urban scenario, come up with a template. How many objects you can expect, how many buildings you can expect on the average, and then create that scenario. And we need to figure out how to model these different lines of sight, different paths. In addition to line of sight, again, line of sight is, you can typically, you may not have a direct line of sight too. Okay? But if you have direct line of sight, you are sure that you get a good signal. Even though it gets other signals from, or signal energy are coming from other paths will add to it, mostly destructively. You cannot assume everything is going to be constructive. But then having a line of sight is important. In fact, that is the reason why you keep cell towers at a height. Otherwise, why do you need, when you say cell tower, really speaking, the tower is just a structure. The reason you are having a cell tower is because you want to put the antennas on top. And that allows us to give a good line of sight. So without good line of sight, you cannot get a good signal. Typically, they are like, they could be anywhere about 100 feet to 200 feet. Okay. Now you can see the very first presentation we talked about deployable communication systems during emergency times. See the value of having a aircraft airlift a base station. So more importantly, the most important result of that is, or consequence of this is, you are getting a good line of sight, especially for people on the ground. If you have a drone at a 400 feet, for example, you got a very good line of sight. Okay? And the distance, there is one more thing you have to think about. If the path takes longer time, the distance is longer, then you assume you can see that power loss is larger, right? But compared to 400 feet, thinking about speed of light, and then thinking about 400 feet or even 1 kilometer, not really a big deal. But the problem is, the path loss is proportional to d squared. So that's where you encounter loss. So how the d actually distance plays a role. Mm, The other thing is that sometimes we know that having a base station at a higher altitude gets you a better line of sight, number one. At the same time, if the distance is increasing, you encounter more loss. So probably there is an optimal height, optimal altitude, where you balance, that you don't lose so much of so much of signal loss, or don't encounter so much of path loss. At the same time, you want to have a clear line of sight. So there is an optimal altitude, and that is another reason why placement of a UAV for aerial base stations is an important research problem. Okay. But here, I'm just showing you, even though we are only looking at one path here, one non-line of sight, in addition to one line of sight, we need to consider practically more non-line of sight. And then we'll get into that. What do you get out of it? We will learn. In the book, actually, this problem is explained very well. The geometry is explained very well by using something called reflection. If you reflect this whole thing on the bottom, then using that geometry, you can compute all these path distances much more efficiently. So take a look at Rappaport's book, please. Yep. Hmm. Hmm. Right, exactly.
So how we reduce that signal from the overlapping or to other message signal or same signal? From how we reduce?
In fact, really speaking, you cannot reduce anything. You can't change the physical phenomena. But first of all, you have to estimate, how long you are going to get these signals. For example, here you're getting one copy, then this is another copy, and then you get more and more copies. So there are some metrics like, we'll going to look at them. Delay spread, that's one that captures how long you're going to get these copies. Okay, that's number one. Number two is, you cannot change the physics. You cannot eliminate them, because you cannot remove the buildings. It's not in our control. But what you need to do, you need to develop the techniques at the receiver to deal with them. Like, for example, multipath, or you can you can design a receiver to effectively collect all these signals, and then see whether you can do something constructively add them. Okay. There is, for example, there is something called rake receiver that does something like this. The second thing is multi-input, MIMO, for example. It also is a means of effectively dealing with this. Okay, so we cannot change the physics, but you can come up with intelligent small techniques to build a better receiver to handle this multipath problem. But I keep telling in my class, multipath is an important problem that in communications, if you ask what is the most important problem, that this is the problem. Okay, but the more you understand, it's basically there are a lot of work done in this field, but if techniques to handle the consequences of multipath propagation is a challenge. So those techniques there are there, but there is more need. But we will talk about the thing that you mentioned just now. All right, here is a interesting thumb rule. It says if the environment is free space, the path loss exponent is 2. We talked about that's the minimum. Okay, so even in what's more important is in free space, that's the minimum loss you can get. But then quickly you can see the worst case is here, somewhere here, shadowed urban cellular radio. In urban setting, this exponent can go all the way from 3 to 5. That means severe loss. 5 means severe loss. Okay, and then other things in general, if there are shadows, means like buildings completely obstructing sometimes. And then in urban, if it is simpler, less complex urban setting, it's anywhere between 2.7 to 3.5. Within building, this is within building. So it looks like within building you are better off actually than obstructed in building, in factories. So look at these first three. So point is, anywhere it can go typical exponent anywhere between 2 to 5. So there is another way to explain path loss. Some of the books, they use a reference distance d0. For example, if d0 could be like 1 meter. So you first of all compute what is the path loss at 1 meter, and then use it to estimate path loss at a distance d. So sometimes in books you can see this model as well. So now I can move a little faster so that we understood the basics. This is called log normal shadowing model. The log distance path loss model does not consider the fact that surrounding environmental clutter. So the clutter means like a lot of buildings also could be called clutter, or maybe a lot of trees, shrubs, those are also called clutter. So basically he is adding a variable, let's say distribute some sort of a random variable that has a Gaussian distribution. So which means that in little more, in complex environments where there is clutter, you need to add an additional term. I hope you see the point, right? So this part is what you already know. This part is you already know. But this part is something additional variable that you are adding to accommodate for complex clutter in the environment. And there are lots of models, but we will probably look at only we don't have to review all of them, but there are a lot of common models. But typically the model, the path loss model depends on the environment. Environment means trees, buildings, hills. So it's not the same. Some people spend a whole lifetime just working on this kind of research. And they say also 3GPP came up with standards for different environments, the parameters that are associated with it. So you don't have to do research from scratch. You can always look at standard models. So for example, if you want to know how to account for rain, how do you account for like clouds, there are standards models that are already developed. In fact, most of the time this kind of research is done by physics people. Okay, yeah. Because if we don't know how, we can't do everything. We start with like path loss models and adding some parameters to account for more complex environment. But it's a physics people who actually study what is the impact of rain. And for example, scattering could happen because of a raindrop. So people spend their lifetimes, as I said, to study this kind of thing from scratch. But fortunately, a lot of work has already been done. All right. Now I will skip some of the slides. Okay. Now I'll need to look into one more deck. More like a research. Part 1 and 2 for the first hour. Here we are reviewing, what are the parameters, what are the some of the basics for this topic. So let's start with the concepts of fading. So term fading refers to rapid fluctuation of the amplitude in a radio signal over a short period of time. And fading is caused by interference between two or more versions of the transmitted signal. So we talked about multiple paths. So multiple paths will cause the interference. So they are not constructive all the time. There is possible that in some cases it is, but typically it is. You can assume that it causes actually a destructive interference. So how is that? So look at the third bullet. At the receiver, radio waves generated by the same signal may come from different directions with different propagation delays and amplitudes and phases. So this is called multipath component. So more specifically, we need to have an idea about how do you account for, or how do you model the propagation delays? And there are very specific concepts that we will be learning. Okay. So, 3 types of small scale fading. One is changes over a small distance or time interval. In fact, time and distance are connected. So, whether you say over a small distance or over a small time interval, both are actually referring to the same. So, one is to do with the distance, and the other is about the Doppler effect. It's more to do with the frequency shift. And Doppler shift comes into picture when you are in a moving vehicle, either transmitter is moving or receiver moving, then you get into Doppler. And the third is generally, there are other things that we talked about, other physical phenomena like refractions, reflections, scattering. So those are also will cause multipath propagation. And ultimately, the most interesting thing is you can model the channel as a system, and it could be depending on how we interpret or how we design. It could be in simplest term, it could be something called a linear system or linear time invariant system, and in general actually it's a time variant. So, but if you oversimplify, it's possible that at least for some short duration, you can model the channel as a time invariant system, and then you can come up with something called a channel impulse response. So, for again just a quick review of for those who haven't done studied this topic from basics. So, you are saying there is a transmitted signal, it's going through a channel, and you are receiving at the receiver. So, one way to interpret this is you are sending a signal through a system, and you are seeing what is the output of the system given this input. So, basically you can explain the channel as a system for which you can derive input-output relationship, and that is typically done in the form of a impulse response. So, basically a channel can be modeled as a system, and its input-output relationship can be explained in the form of a impulse response function. Okay. I think that is the that is the way we can interpret. And now, what are the factors that will influence small scale fading? Small scale fading refers to small fluctuations over small intervals of time, or fluctuations over small intervals of time, or small distances. So, what are the causes? What are the issues? One is multipath propagation, which we already spent a lot of time on, and then there is the vehicle of speed of a mobile. So, obviously in this case we are saying we know that cell tower is not going to move because cell tower is fixed on the ground. So, what is moving? The receiver. Your phone is moving because you might be in a car, for example. But when you go back to lecture 1, is the other way. If you put the base station on a cell tower, so on a drone, then the transmitter is moving, or cell tower is moving. And even more interesting is, in the case of satellite, LEO satellite, is a satellite that is moving. So far, for ground communications or terrestrial communications, we assume that cell towers are fixed. It is the phone that is moving, or the user that is moving. Okay. But some of these ideas are you can use the same concepts, with of course cognizant of the fact that the speeds are different. The speeds for when you are moving on the car is different. When you are talking about drones, the relative speeds are much higher. When you talk about satellites, what speed they are going to fly? LEO satellites that fly around 26,000 kilometers per hour. So when you think about Doppler shift has to be accounted for satellites. So we don't consider that much of we not, or even the Doppler shift is encountered, which happens even when you talk about communications with drones, or even with cars. But those were already you can compensate them as the receiver. 3GPP already developed the compensation techniques for those Doppler shifts that you encounter when you are traveling in a car, or to some extent for drones as well, but not for satellite speeds. For example, research showed that we also have done a lot of work that OFDM cannot handle the Doppler shifts caused by LEO satellites. Okay, even though you can try to use OFDM technique for satellite communication, it doesn't work. It's not guaranteed to work because it's the Doppler shift, that compensation techniques for addressing Doppler shift is not sufficient for satellite speeds. Okay, so which means that there is room for doing more work, both research and development. And interestingly, recently there is a new modulation technique that is OTFS, called orthogonal time frequency space modulation plus multiple access technique, and that seems to be, you can design that modulation technique in a way that is immune to Doppler shift. That's a very powerful thing. Okay? So in fact, a lot of people worked on it since at least for about 6-7 years on OTFS. It originally, the paper came out around 2018 or 2017. So a lot of work has been done, but it didn't get into the standards. The reason is even for 6G, potentially maybe it may come in 6G, and the reason why this OTFS didn't get into 3GPP so far is because the industry says that they already spent a lot of money and efforts, and then in 5G, and then they still want to make sure that their investments are protected. So it will take a while for new techniques to get into standards. The other important thing is to learn here is, you may come up with a great idea, but it may not see the light unless it gets into standards, and that depends on other factors, not just about technical talent, technical superiority, but sometimes it has to meet the requirements of the industry. Okay, let's look into quickly the other things. So here are the factors that we need to consider. One of them is speed of the vehicles, other is of course bandwidth, and other is not only the speed of the mobile receiver but also the surrounding objects. Yeah.
So OFDM works for one of the transmitter receiver has to be stationary, the other can be.
Yeah, but in general,
Both are moving, you cannot.
no, not that. Actually, no, we can typically, let's assume that they are like, we only consider the relative speed. So we are okay if both are moving also. But the thing is,
Both are moving at different speeds.
different, yeah.
Then the relative motion will be something else.
Will be higher, or yeah. But the way they do something called pre-coding technique. Yeah, basically you are giving some sort of a gap. Yeah, right. Yeah. And the pre-coding technique, it depends on how much Doppler shift you are expecting, but the kind of pre-coding that we have, the length of the pre-coding is not enough, not sufficient to handle larger things. Yeah, larger Doppler shift.
If we try to increase the prefix and all, the data packet
Will become smaller, and then at least at this point, the standard is did not. There is a limit on the pre-coding line, and if you arbitrarily include, there are other issues that we encounter. Yeah.
So the cyclic prefix will not.
Say again.
The cyclic prefix.
Yeah, cyclic prefix will work for certain length, so smaller Doppler shift. But I believe the Doppler shift that we encounter for satellite speeds is almost like 200 up to 200 kilohertz. So for that, I don't think OFDM. Yeah. But there's a good solution, but it's not yet gotten into the standards. So OTFS, if you design those resource blocks, like the resolution of time frequency blocks, if you design them appropriately, then the impact of Doppler shift is not there, won't be there.
FPM also we do time.
Yeah, it's the same. Yeah, it's right. That's true. It is the same, but you need to design those resolution levels, expecting what kind of Doppler shift you can handle. In fact, probably we'll talk about that in the last class on the last day. So this gives an idea about the idea of Doppler shift in little more specific details. So what it refers to is, because of Doppler shift, your received signal frequency, especially when you are in vehicles, because of motion, due to motion, is going to be different. Your transmitting frequency is different, received frequency is different. That means your receiver won't work. Receiver reception techniques or demodulation or decoding techniques won't work because you're getting a different frequency. And not only that, it will also cause intercarrier interference. This causes interference in terms of frequency terms. Okay, so the shift means frequency shift. It's proportional to the speed and direction of motion of the mobile. And in simple terms, this diagram explains very, very well. So when you are the original path, when you are here, when the vehicle is here, this is the path. Think about this is the source or transmitter. You can think of a 2D. Even though you are seeing this picture like this, think about like a 2D. So there is a source, and this is the receiver, and this is one path. And then when your vehicle is moving to Y, it has a different path. So in this case, you have different longer length, and now it is shorter length. Or if you go the other way, if the vehicle is going the other way, you will see again the path is going to be increasing. Here, if you from X to Y, the path length becomes shorter, but if you go the other way, it increases. So based on that, if you can compute the delta L is a difference between the two paths, X and Y. And if you put that, then delta phi, which is a phase change, you can compute phase change equal to 2 pi delta L by lambda, and that explains the connection between or the relation between the phase change because of the change in location. And it of course it depends on the speed of the vehicle and how much distance you travel. But again, this is a fundamental problem, and it is in many books you can see this. And okay, now here is what really we want to do, what we are interested in. So with all this, what we really want to do, we want to develop a channel model. So what do you mean by channel model? You want to bring the input-output relationship between the transmitted signal and the receiver signal. So that is the essence of all we talked about. Okay, and how do you do that? What really we want to do is express that relationship in the form of a channel impulse response. So what do you mean by channel impulse response? If you have a system, and if you give input as an impulse, if impulse is your input, what would be the response? It's very simple. Yeah. But then you need to make a connection to what we learned so far and understand how do we build such a impulse response. And there are a lot of papers on it, so it's not a difficult thing. A lot of work has been done, but our goal is to actually get an idea about how do you build a channel model. Okay? So channel model is ultimately we want to come up with an impulse response of the channel that explains the relationship between input and output. X is the transmitted signal, Y is the received signal. Okay, so whether it is air to air channel or air to ground, all we want to do is express that or model that relationship in the form of a system, and when you do that, what happens? What is the result? You can say if you say H is our channel response, impulse response, is a function of distance and time, and they say later, some of the detailed examples. Obviously, distance and time are related, especially if the vehicle is, or the movement is constant. Suppose the car is moving at the same speed, constant speed, then it gets simplified. But in general, it's a function of distance and time. So look at this. This is the key. If x and y could be expressed as in the form of impulse response, then y could be written in terms of x convolved with the impulse response. That is the essence of this, whatever we learned so far. So our goal is to, in whatever channel model we are building, are interested in, can we express that as an impulse response? Can you describe the channel as an impulse response, which is true? And then the other thing is it time variant or time invariant? Okay. Because if you simplify the model with lots of assumptions, you can say you can express that as a time invariant system, but in most scenarios it is time variant. Okay. And can you see, if you understand what is a causal system, then you can see how this simplifies. The upper bound becomes t instead of infinity. If you know the definition of causal system, think about it. Probably will give you that as a question mark in the homework. Yeah, I won't get, it's just some small thing, but if you are able to understand that, that's good. Yeah. Then, in order to build such a response, such an impulse response, what kind of things we do? For example, as of now, my students and I are working on developing a model for air-to-air channel, air-to-air communication. That means drone-to-drone communication. Okay. So to do that, one option is start with simulations. So as I said, we use a tool called Insight. So what do you get from the experiments? So one of the metrics that we need to measure through simulations is called power delay profile. And by the way, I'm not an expert in channel modeling. So what I do is I found a professor who has spent his whole lifetime on channel modeling. Okay. So he is helping me. I'll bring his name. I'll discuss that when I show you in the second half of the lecture after the break. So if you don't know something, what do you need to do? If you're not, because we can't be experts in all fields. So what we do is you need to collaborate with somebody else who is very specialized, who has expertise in that field. So for example, in many situations, sometimes we get into some mathematical scenarios, and for which we need some help. So we go to mathematicians, mathematics professors. It happened to me many times. In fact, like graph theory is one example. The other example was I was doing some detection and estimation problem, and such problem has not been solved before. So we reached out to I'll give a little bit of context to that. We were working on ranking a sensor observations, because some of you are working in sensors, I can tell you. We are working on something called ranking the sensor observation, because suppose you have thousands of sensors, and you are supposed to communicate with the faraway sensor fusion center, then it's difficult to collect all these number of sensors and transmit all of them all the time. So one idea is that we came across is, how about you pick top 10 observations that are important, significant for the whatever phenomena whatever research you are doing, whatever phenomena you're trying to observe. So one question that we have is, what is the PDF or probability distribution function associated with the first rank? So look at this. Even you assume that the sensor observations are following some Gaussian distribution or something, but what we are interested in is, what is the nature of the first rank? So we are only looking at the rank 1 of observations or highest ranked observation, and we want to study what is the PDF corresponding to that. And I didn't know how to work on this, so we reached out to mathematics faculty. All right. So one of the metrics that we need to work on is something called power delay profile. What do you mean by power delay profile? It addresses the small scale fading, and of course also the distance too, but more primarily it addresses the small scale fading. So PDP of a channel or power delay profile of a channel is found by using the spatial average of these what you call, what is HP? HP is the channel gain. H refers to generally H of t, tau refers to channel gain. Or in other words, you are looking at HP stands for the, I think it's sufficient, it suffices to say we are referring to channel gain. So if PT is the, and it has two parameters, t comma tau. So tau refers to the delay, t is the transmitting time and tau is the delay. So what we expect is when you transmit a signal, you are going to get multiple copies over certain duration, and that is your x-axis. In y-axis, you are saying what is the received signal strength or received signal power for each of these delayed versions. So in general, this is the meaning of this. If PT is the, PT has a, transmitted signal with a power P has a time duration much smaller impulse response. Actually, think of PT like a pulse. So if you have a small pulse, and that's how you transmit anyway. Remember, when you're transmitting, you're not just sending, you're holding the signal for a while. So here PT actually refers to the pulse. And if the duration is smaller than the impulse response of a multipath channel, when you say, what do you mean by the smaller than the impulse response of a channel, you're talking about how long you are getting the delayed versions of the signal. So when you send one signal at the transmitter like a pulse, you're going to get multiple copies. But how long? That is the y-axis. That's the x-axis. So they say the received power at various delays can be estimated or measured by technique called channel sounding, and through simulation you can actually plot. So for example, in our case, we haven't modeled anything. With simulation you don't have to model anything. Well, let me step back. You design the terrain. Like for example, we create buildings. You define how many buildings are there, at what heights. Those we do, but we are not writing any equations. Okay, we're not. That's what I meant by we don't not building anything. So you create the environment and then decide the distance between a transmitter and receiver. Then all these reflections will happen. The tool will take care of it. So, and it will give you this data, this power delay profile. So all you need to do is how to measure the power delay profile and plot the graph corresponding to the power delay profile, and that's what we can do through simulation. This is one of them. This is one major parameter that we need to do. So initially we are doing through simulation, and later we can come up with a theoretical model, because we know what is power delay profile, power delay. In fact, in simple terms, you're measuring for all these non-line of sight components. For each of the non-line of sight components, which will reach the receiver at different times. For each of those non-line of sight paths, you are measuring what is the power.
When we send a sync pulse, at the receiver you get, when we impulse pulse,
Yeah.
receiver we get a sync pulse.
You get a multiple copies of that.
And all the things we take it and plot it like that.
Right, exactly.
And now we want that to die off faster.
Yeah. So yeah, that's true. That's actually true. In fact, when we one way to interpret that is the point that you mentioned is to begin with, you get the line of sight, you get a best signal, and then it tapers, right? So the question is, when do you stop? One way to do that is, in fact, again, my professor, my collaborator told me that when we actually doing the simulations, we got about 25 paths, and then think about it, 25 paths for a typical scenario. I'll show you what scenario I did, and out of that, one thing you can do is If the received power is, let's say, below certain threshold, you can ignore. So in our case, maybe about 15 things you could ignore. Even you don't ignore, the signal will be so small at the end. So basically it tapers drastically. That's right. Yeah, that's true. Now, the idea is if it is too small, like below -100 or -110, even it is there, it doesn't really impact much. But you are right, in general, it can go for a longer distance. So as I said, 25 paths, 25 non-line of sights we were able to see, we saw. But generally the idea is to understand how to measure this, and more importantly, how to use this to develop a channel model. In fact, we are not even there yet. I'm just showing you. I will show you in the next hour what all we did, but we are still in the process of developing the channel model. So we'll do very quickly, and then and how do you measure this? These are called channel sounding techniques. In simple sense, we won't need to go through in detail, but in simple sense, you're trying to send like a pulse or an impulse, and then trying to measure in different regions, different locations rather, to account to you are measuring the received power at different distances. So that's the basic idea of channel sounding technique, but these are the little more detailed techniques. Now, for example, here is one. One technique is called direct RF pulse system. So you are transmitting a pulse like this to the receiver, and then at the receiver the signal is amplified and detected using envelope detector. If you remember any demodulation technique, amplitude demodulation technique, you know what is envelope detection. And then it is detected and stored in the receiver, and then you can average the received power at over the time. So that means over different quantized delay values, you are measuring the received power. So I think that's enough for us to understand the concept of power delay profile. Okay, you are basically capturing the received power at different delays, and the delays are coming because you have multiple non-line of sight, and the longer the non-line of sight, the longer delay it will encounter. And there are also a few more terms, so I'll skip this, and then this is more important. What kind of parameters we are interested in? We talked about what you call power delay profile. There are a few others. Yeah, we can. What's the time? Okay, 11:30. Yeah, let's take a break. So I'll wrap up this in the second half, and then go into air-to-air channel modeling. Yeah.